Welcome to the online lecture of CSE 4551 Computer Graphics and Multimedia. This is the second part of the two-part lecture on ray tracing. Previously, we had talked about uh, we introduced features like shadows and reflection into our ray tracer. Now we start our discussion with how we would add refraction. Ref, uh, Reflection, the one we talked about before, allows us to render mirror surfaces in our scenes. And now we introduce refraction into our ray tracer so as to be able to render objects like windows and fluids. The idea is to cast a ray from the camera, and when we find an object that it intersects with is a refractive object. The material of the object must define itself to be something like a glass window or a water-like uh, object material. That is, it must be refractive, and then from that point of intersection we cast another ray in the refracted direction, and we multiply a transparency coefficient kt, similar to how we did it for mirrors. We multiplied with a ks, if you remember, so as to control what would be shown here, whether it will have some kind of tint or not, some metallic tint or not. It may be reddish here, it might not show the actual color. So those things were handled using ks, a reflection coefficient. So similarly, we will have transparency coefficient kt, and we will use it so that we can control whether the object seen through the glass or window or fluid will be in its actual color, or will its color get dampened because of the color of the glass or fluid itself. You can understand why we need to set this kt. If you think what you see through a glass of lemonade, objects seen through a glass of lemonade will not be seen in their actual color. Rather, it will get changed a bit. Maybe it will look a bit yellowish or something, or a bit greenish. So that is why we need this transparency coefficient. Okay, now recall what we know about refractive indices from our intermediate level physics. First of all, refractive indices are properties of the material itself. Uh, each type of each different type of refractive objects can have its own refractive index, which we denote here as eta. And this is basically the ratio of the angles the incoming and outgoing light rays make with the normal at the point of intersection. That means the ratio of this angle by this angle. Uh, Actually, it's reverse. It's the outgoing rays angle divided by the incoming rays angle. Sine of the outgoing rays angle divided by sine of incoming rays angle. That is what we denote as the relative refractive index with respect with this medium, for this medium with respect to air or another medium. So next we refer to the next slide, this particular slide, where we see a rather complicated derivation of what the refracted ray vector should be obtained as. Notice how the incident ray this is the incident ray vector, and this is the refracted ray vector t. The incident ray vector is I. Here we derive how t will be obtained from I when these things are known. The normal vector and the components, different components are known. So notice how the incident ray vector I can be decomposed into horizontal components, horizontal component and cos theta. For this ray, this is actually the horizontal component, even though for us it looks to be vertical. But when you consider this ray and this particular angle, then this is the horizontal component and this is the vertical component. So the horizontal component is n cos theta I, and vertical component is minus m sin theta I. Minus m, why minus m? Because this was supposed to be m. If you define this to be m, this to be n, then this should be minus m. So its horizontal component should be minus m times sin theta I. So this is how we got this particular thing. And then we can express m as this ratio. Just put m here and divide by sin theta, or just take it there and divide by sin theta. So we get this thing for m. So just like we decomposed the incident ray vector I, we can similarly decompose the refracted ray vector t as t equals to minus n cos theta t plus m sin theta t. Now put the expression of m, the one we obtained here, replace m with m here with this right hand side, and we will get this particular expression. And then you can actually see that sine theta t divided by sine theta I, this particular thing is actually what we previously know from Snell's law as the relative refractive index. So replace this thing with eta r or nr. Just for simplicity, we are not referring to this as eta from now on. Suppose this is nr. So replace this ratio with nr, and now you can do some extra uh, algebraic manipulations here. Take n common, and then replace cos theta t by 1 minus sine square theta t. You can also change sine square theta t to be nr square sine square theta I, because here we have sine theta t. If you multiply sine theta I, take it on this side, then nr sine theta t becomes nr times sine theta I becomes sine theta t. So sine square theta t should be nr square sine square theta I. This is how we got this particular part. And in this way, by doing some more algebraic manipulations, trigonometric manipulations, you can actually finally reach up to this stage. And then we notice that we can replace all the cos theta I here with n dot theta, n dot I. Since the dot product of n dot I would actually be n magnitude of n times magnitude of I times cos theta I. If you actually see the dot product of n and I, you would see that this would actually be obtained from what we know before as magnitude of n times magnitude of I times cos of angle between them. Since magnitude of n and magnitude of I are both 1, considering both of them as unit vectors in this direction, their magnitudes are 1. So cos theta I is basically equivalent to n dot product with I. So this is how we obtained this final form for t, the vector t. So now we know how the refracted ray will be obtained, as long as we know what the incident rays vector was, what the normal vector was for this surface. When all these things are known, then we can actually find t. The reason we went through such a hassle to convert all of these things into this form is for eliminating the trigonometric functions from the representation of t. Notice how there is no trigonometric function here, and what we have here are all simply dot products, and everything here are just either a scalar value or a vector. N here is a vector, I is a vector, and nr is a scalar. So all these things are either scalars or vectors. And what we know is that the graphics engine or any kind of 3D engine can actually handle dot products, matrices, and vectors very fast compared to these trigonometric functions. So that is why we converted this whole thing into this form. So now that we have a representation for the refracted ray t, we can notice that there is a term with square root in here. So what does it mean for the square root to be negative? If somehow the expression inside the square root evaluates to a negative value, then we will have an imaginary number here, right? Which actually corresponds to the phenomenon of total internal reflection. That means there is no refraction, only reflection. So this and these images show some examples of what total internal reflection would be like. This was a glass-like material. Passing light through it got made it to be refracted, but at this point it actually caused it to get totally reflected. No part of it got transmitted through this to the outside portion. Similarly here, when a scene like this is being rendered, where the camera is under a dense material, transparent material like water, then this particular effect can actually be rendered using a phenomenon of total internal reflection. This is one of the cases where we will need this. Okay, so another thing, important thing to keep track of is whether we are actually entering or leaving a refractive material, because a ray entering a glass, for example, would get bent towards the normal right after hitting the surface. For example, if the ray was coming from air to glass, suppose this is glass, if the ray was coming from air to glass, then at the point of contact of the at the surface, the ray would get bent towards the normal. If this was the normal, the ray would get bent towards it. On the other hand, if the camera was inside a glass, a dense material like glass, and the ray was supposed to be casted from the glass surface, from the glass material towards a less dense material like air, then the ray that would be cast should be driven away from the normal. So these things require us to keep track of where the casted ray originated from. So just always handling the ray in the same way will not work in all cases. We need to know actually whether the ray originated from the refractive surface or whether it is going towards a refractive surface. Okay, so next we move on to some discussions about realistic scenes. In this particular slide, think about these images. We already saw these images before. This particular image was also there in our previous lecture when we were talking about reflection. These images are not very realistic and have a kind of virtual feeling to them. You can already directly surmise from the scene, from the images that you see, that this is not an image of a real life this does not look like an image of a real life object. So what could be the reason for this? The problem here is that objects shown here are perfectly refractive, and for this case this is a perfectly refractive and this is a perfectly reflective substance. Although in real life no object like this no object should behave like this, since no surface is perfectly smooth, right? So in order to render objects more realistically, we need to account for glossy reflection or refraction. So how do we add glossiness to our ray tracer? Remember that before, when we were casting a ray and it got reflected or refracted at the surface of the object, for example, in this case it got reflected, and if it is a glass-like material then it would get refracted. In both cases, notice that for one primary ray we cast exactly one reflected ray or exactly one refracted ray, resulting in perfectly specular reflection or refraction. Now for every single primary ray intersection, if you were to cast multiple rays at a small theta plus minus theta angle from the point of intersection, then and then we took the average of their shading results, whatever they got shading that they would generate. If we averaged it, then we would get a non-ideal glossy reflection or refraction. The use of glossy reflection and refraction results in a more realistic looking effect as seen here. As you can see, this looks a lot more realistic than the one we showed before. This particular reflection and this particular refraction, those were not realistic, but this one seems a bit more realistic because this actually simulates what real world objects look like. So similar to how non-ideal reflection or refraction looks more realistic than the ideal ones, we can also make shadows look more realistic by considering soft shadows instead of hard shadows. Remember how we cast a single shadow ray towards each light source for intersection of every primary ray in our previous lecture. This results in a shadow which is plain black or gray, like this, thus giving a hard shadow and making it look unrealistic. But if we cast multiple shadow rays and took the advantage of average of their illumination values, and then we could have a more realistic looking soft shadow that is dark near the center part of the shadow and is a bit blurred near the edges of the object, and this looks more realistic compared to this hard shadow. As you can see, this one seems a lot more realistic. So now we come to the final topic of this lecture, that is ray tracing, recursive ray tracing. Refer to the online the algorithm structure for ray tracing shown in this particular slide, where we have included all three features into our ray tracer. In our previous online lecture, we already talked about how to introduce shadow into our ray tracer, and also how reflected rays would be handled. Now we talked about how refracted rays would be handled. If you combine all of them, this is what you would get, the general structure of the pseudocode, the algorithm. And notice that both the reflected ray and the refracted ray ask for us to recursively call the same ray tracing function again, right? So there can be some scenario where this recursion goes on indefinitely, causing our system to crash. Think of a scenario where there are two plane mirrors facing each other, similar to what we see in the barber shop. Such a virtual scene will have rays cast onto one of the plane mirrors, then another ray would be reflected towards the other plane mirror, calling the ray trace function again, and that would again call itself, right? Again it would get reflected and it would call itself, and this would go on infinitely. And if it was if it was a game or a particular scene that you are rendering, this will cause your computer to crash before it even gets to render the final scene. So the way we handle this is to define a limit for the number of bounces a ray can have, which we denote here as the recursion depth. Also, we can consider the ray contribution, and we prevent calling the ray trace function if we see that the scene generated by the current ray hasn't contributed much after what the previous bounce had done. Suppose you are considering thousands of bounces and you saw that the recent 1000 bounce didn't, or the recent 999th bounce produced such a image that the next bounce didn't make much of a difference. Then you can actually stop the tracing of the ray there, and in this way you can actually avoid a infinite loop. Okay, now we move on to a structure called ray tree. The recursive ray tracing that we talked about earlier leads to this particular structure called ray tree. Notice how each ray cast from the camera gives rise to 3 rays, considering ideal shadow, reflection, and refraction. Like we talked about before, in this particular case, we can have multiple rays in order to introduce some realistic blurry effect or some kind of glossy reflection or refraction. But now let us consider this general ideal case, the simplistic case, where for every primary ray we have a single secondary ray for reflection or refraction. So if we consider that, then you can see that for every for every ray coming from the camera, you have 3 rays generated at the point of intersection. One is the reflected ray, this is the light shadow ray towards the light source, and this is the refracted ray. So these 3 particular rays, the blue, green, and red, are generated at the point of intersection wherever the camera ray, the initial primary ray, gets intersected. So also notice that each of these rays can in turn create all these rays again, all these 3 rays again, or maybe 2. For example, if this was not a refractive material, only reflective, then it would not generate T, that is the refracted ray. It would generate the other 2, reflection and shadow ray. So in any case, the thing is, each of these rays can generate even more rays, thus giving rise to this particular tree-like structure, as you can see here. And it is evident from this particular, we can also visualize from this particular scenario how a single image pixel ray, this white ray is the single pixel's primary ray. And what this single pixel's primary ray can do in a scene, this single pixel can generate so many rays. It can produce a shadow ray towards the light source, it can produce a reflected ray and a refracted ray. This refracted ray itself can produce all these 3 rays. So you can all this is actually evident that the computation required here increases exponentially, which is why ray tracing is a very slow process, although it generates very realistic looking scenes. You can actually see that this would get very complicated very fast. The number of cases here, the size of this tree would increase exponentially. So there are actually ways to make ray tracing work faster by introducing some specialized acceleration structures like KD trees. But these are beyond the scope of this lecture. Anyone interested in this can check out bounding volume hierarchy and how KD trees work. But suffice to say, this will not be part of our exam, so you need not worry about this. So this will be the end of ray tracing. Thank you for your attention.